So on the last little lecture, we talked about we did a quick survey of the environmental regulations that have done so much over the last 50 or 60 years to clean up our air and water, drinking water, and so forth. And I mentioned a couple of these things that I'm about to talk about, and some of them I haven't. So I'm just going to go through them. So here's the book, Silent Spring. This is one of the most important books in the environmental canon. And remember, it's about the collapse of bird populations owing to the use of a chemical called DDT. Here are some eggshells that have collapsed and the young birds have died, and here's some cracking that you can see. But this led to a collapse of bird populations, many types of bird populations, until it was outlawed. I think I also mentioned the Cuyahoga River in Cleveland on fire. Here's a photo of it. You can see there's a bridge on the left-hand side, and you can see there's oil slick out here that's burning. Well, you don't want your kids to play in that, and you don't want to fish in that, and you don't want to drink water from that. And it was basically used as an open sewer, as a lot of lakes and rivers were around the United States and around the world, until the 1960s and 70s began to improve environmental regulations. Here we go. Here's the Don't Mess with Texas ad campaign that has, again, just been remarkably successful in Texas, but also just public awareness of roadside littering has dropped this tremendously. I mean, this isn't a massive environmental problem, but it is unsightly. Massive environmental problems, however, do look like this. So here we have in the upper left, we've got sort of industrial effluent just being dumped directly into a river just to get rid of it. No pollution, no pollution control, no remediation whatsoever. Here we see a stream that's been completely destroyed by organic compounds being dumped out of some sort of factory. And here we have a lake someplace that's just completely overflowing with plastic bottles and all sorts of stuff. And this was more or less not uncommon prior to the era of environmental regulation. So there were two major issues that happened, environmental issues that happened in the middle and latter part of the middle part of the 20th century that are worth talking about. One is lead in gasoline. So lead's a neurotoxin, and as you may know, lead is banned in paints and it's banned in pipes. If you ingest too much lead, it can kill you, but it can also, in relatively small amounts, can depress your IQ and cause all sorts of other neurological problems. So it's a real issue, and it was good that we got rid of it. But lead used to be in gasoline, and it was added to gasoline thanks to this guy on the right, Thomas Midgley. He's the one who came up with a compound called tetraethyl lead, and it was designed to help car engines run more smoothly. It turns out that ethanol can do the same thing. Corn or any kind of sugar-based alcohol like that. Anyway, Thomas Midgley created this, and oil companies and chemical companies began making a lot of money because this was an additive that everybody wanted in their gasoline in their car. This guy on the left, Claire Patterson, is an Iowa boy. He was actually the scientist. He was a graduate student at the University of Chicago. He was the first person to date meteorites using uranium and lead, and as a result was the first person to figure out how old the solar system was. It's a pretty good PhD. Anyway, while he was doing research into lead isotope concentrations, what he began to find, particularly looking at meteorites, was that the lead concentration on the outside of the meteorites was very, very different than the lead concentration on the inside. And he really reasoned that there must be a lot of lead in the environment. And that led him to recognize that there was lead being spewed in enormous quantities, of course, from engines, car engines, and that it was accumulating in unprecedented amounts in the environment and causing all sorts of problems. Here are a couple of old ads advertising this leaded leaded additive that you put in your car, keep the engine from knocking, that sort of thing. And so one thing that scientists did, including Claire Patterson, is they wanted to know how much lead was in the environment normally. So they went to places like Greenland, and they took cores of the snow and ice. And you can count the layers; they're annually layered. So you can start at the top. Say this was done, I don't know, 1960 or something. So you start at the top and you just go down, and each year that you go down, or each layer that you go down, is another year. And they sampled the ice and snow, and they measured the amount of lead that was in it. And what you can see is basically that the lead concentration has been rising in Greenland pretty steadily until the early part of the 20th century, when lead started being used as an additive gasoline, and then it shoots up like crazy. Let's see. So it turns out that Claire Patterson was vilified by the companies that he was fighting because he worked so hard to get lead out of gasoline. And one of the biggest reasons that he ended up winning and that we don't have lead in gasoline anymore is because of the Clean Air Act. This is a photograph of Los Angeles in the 1970s. And the smog was at times really just unbearable and incredibly unhealthy. So people were clamoring for clean air. And the way that you get rid of that smog, the smog that's coming out of tailpipes, is you add what's called a catalytic converter, which is a little instrument that sits inside the car and basically reduces the amount of pollution that gets emitted out of the tailpipe. Well, the catalytic converter was being clamored for, obviously, because people didn't want this smog anywhere. But the catalytic converter didn't work well with lead gasoline. The lead interfered with the catalytic converter. So the catalytic converter helped to usher out the era of lead gasoline. Although the 1970 Clean Air Act was going to do that anyway, but the political resistance was dampened because of the need to get rid of smog in big cities. All right, so lead came in the early 20th century and was banned began to be banned in 1974, and was finally out during the Reagan administration. But unfortunately, lead lingers in the environment for a long time, and we have much more lead in our systems than our great-grandparents did, and our kids will, and so forth. So it's around largely to stay. Something that we've had a little bit more success with is the ozone hole. If you don't know about that, in the early days, styrofoam and the little gases that you'd put inside spray cans, you'd shake them up, and then you push the button, and the paint would come out, whatever, the deodorant or whatever it was. The little gases that were in there that came rushing out, that brought the paint out with them, were these little kind of molecular springs. And they were used in air conditioners and refrigerators and so forth. And for a long time, the chemical compound is called a chlorofluorocarbon. And basically what happens, right, is that you can compress these things and they go into a liquid. They have a very high vapor pressure, though. So whenever you expose them to a greater volume, they want to rush out of the liquid phase into the vapor phase. And if you're pushing down on the top of a spray can, those gases come rushing out. And if there's paint in the bottle as well, in the can as well, they bring the paint along, or the deodorant, or whatever it was. And for that reason, because they want to expand, and you can then compress them back into a liquid, and they want to expand, they're really good in refrigerators as well. So there was a big need for something like CFCs, chlorofluorocarbons, because in the old days, refrigerators and air conditioners were running on things that were flammable. And CFCs, apparently, when they were invented, were inert. They were chemically inert. So you could hold them to a flame, nothing happened. They didn't hurt anybody, they didn't burn anybody, they didn't poison anybody. So they were kind of the wonder compound. This is a picture of a hospital that caught fire. I believe this is part of a hospital that caught fire and burned and killed a lot of people. And it burned because the air conditioning system, which again was using these flammable materials, ignited and blew up. It's a big problem. So who invented CFCs? Thomas Midgley, the same guy that invented the lead additive to gasoline. Bill Bryson, who's a writer, famous travel writer, and another Iowa guy, once said that Thomas Midgley has done more to harm the environment than any other human being in history, and he might not be wrong. He invented the lead additive to gasoline, and he invented CFCs, which, as we will find out in a minute, began to destroy the ozone hole, or the ozone layer. So instead of Claire Patterson opposing Thomas Midgley, now we have two chemists, Molina and Rowland, and they won the Nobel Prize for Chemistry for figuring out that these CFC compounds, these chlorofluorocarbons, were not in fact inert all the time under very, very unusual circumstances. And this generally happens over the Antarctic in the summertime, when you have very, very cold temperatures, but lots and lots of sunlight. The CFCs actually stop becoming inert and they start eating ozone. So here's a graph of ozone. Ozone is a chemical composition of O3, it's just 3 oxygens bonded together. And when its ozone is down in the lower levels of the atmosphere, in the troposphere, it's a problem for us. It's not good if you breathe in a lot of ozone. It's a consequence of it's part of smog and so forth. But when you rise up through the atmosphere, ozone levels increase dramatically in the stratosphere. And it's here that stratosphere acts like Earth's sunscreen. So the ozone that's building up and lingering in the stratosphere, this is all natural, absorbs some of the ultraviolet radiation coming in from the sun, and the kind of UVA, UVB, the kind of ultraviolet radiation that could cause skin cancer and some mutations on living organisms, gets filtered out in the atmosphere. So that's a good thing. So this is how ozone is produced, right? So you have this high energy that takes oxygen, which is normally O2, 2 oxygen molecules, and it breaks them apart. And each one of those free oxygens very quickly may bump into another O2 molecule, and what you end up with is O3, which is ozone. Now, when CFCs are in the atmosphere over the Antarctic, you have that same sort of high energy radiation that strikes a CFC molecule, and it splits off a chlorine, and chlorines are very reactive molecules or atoms. So if the chlorine bumps into a molecule of ozone, it strips away one of the oxygens, forming a chlorine monoxide and leaving just good old-fashioned oxygen around, right? The thing that makes CFCs so damaging is that one molecule of CFC, if it splits off a chlorine, the chlorine doesn't just rip apart one oxygen atom, because what will happen is when if another free oxygen bumps into this chlorine monoxide, the 2 oxygens will combine and the chlorine will be splintered off and free to go find another ozone molecule. So one chlorine can actually break apart many, many, many ozone molecules. And so these things are really voracious, and they began to decimate the amount of ozone that existed only over Antarctica. And you might think, well, what's the big deal if all the ozone is being destroyed over Antarctica? We don't live in Antarctica, right? Well, that's a little bit like saying, who cares if we pull the plug at the bottom of our bathtub, right? We're not sitting down at that end of the bathtub, so we'll be fine. Well, in fact, the ozone levels in the entire planet, even though they were being destroyed over only Antarctica, ozone levels over North America, over Europe, over Australia, those places were going down, 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 down every year. And as a result, projections were we were going to see massive increases in skin cancer rates and all sorts of environmental consequences if nothing was done. So here is a sort of a weird image of the Earth. This is based on satellite imagery, but this was the size of the ozone hole in 1981. By 1991, at its maximum size, this is in the same month of October, you can see it's much, much bigger. Ozone's measured in these Dobson units, right? So what did we do? Well, there was some resistance to doing anything at all, because the administration at the time, the Reagan administration, had some very, very pro-business cabinet members, including the Interior Secretary, James Watt. And when I was in high school, there were all these stop signs all over everywhere that had Watt written at the bottom, so stop Watt. But he was a very, very pro-business guy, and at one point was asked what people should be doing about, a new world with higher UVA and UVB concentrations because of the loss of ozone. And I think it was Water, maybe it was Reagan, basically said, we need to wear hats and we need to wear sunscreen. We got to deal with this, rather than dealing with the problem, which was reducing the amount of CFCs. Oh, here we go, suggesting hats wearing sunscreen. So this was the Interior Secretary, Donald Hodel, who said that. Okay, so luckily, Congress and the rest of the world were a little more proactive than other members of the administration. And the Montreal Protocol was signed. I think it was actually signed in 1989. So it was actually signed by George H.W. Bush, the president between Reagan and Bill Clinton, who was Reagan's vice president. And basically what it did was it began the immediate phase out of chlorofluorocarbons, and they were replaced by still problematic, but much less problematic varieties of fluorocarbons, chlorofluorocarbons called HCFCs. But this is not a great image. You can kind of see this is basically, these are these are Dobson units. This is the amount of ozone, right? So there's a lot of ozone. This is 1960, 1970, 1980. You can see basically this big drop in the amount of ozone between about 1970 and 1990. This is when 1989, that's when the Montreal Protocol was signed. And within just a couple of years, look what happens. The amount of ozone over Antarctica in the winter begins to stabilize, and it begins a very, very slow, and it's been a very, very slow, but it has been a slow reversal and come back. The reason that CFCs were able to respond so quickly to the Montreal Protocol is because they have what's called, they have a very short, what's called atmospheric residence time. So when a CFC molecule is released, it doesn't stay in the atmosphere for very long. So when you stop putting CFCs up into the atmospheric concentration begins to level off and decline. And you can see that here, right? So where are we? 1976, I can't even read that, 1992. Okay, so here is when the Montreal Protocol was signed in 1989, and you can see that CFC levels begin to plateau right away, and CFC 11 actually begins to decline. That's what you want to see. CO2 levels are different. They're trickier. And the reason they're trickier is that CO2 has a very, very long atmospheric residence time, decades, centuries in some cases, right? So when CO2 goes up there, it's there to stay for a long time. And so even if we, speaking of global warming, even if we were to stop putting carbon dioxide into the atmosphere, we wouldn't expect it to start coming out in any, any realistically important way for many, many decades, unless we figure out some sort of chemical process, which may be where we have to go to actually pull the CO2 out. But just because we stop putting our foot on the gas with CO2 doesn't mean we're going to slow down. When we stop putting our foot on the gas with CFCs, we instantly began to turn around. I'll post these to Moodle, so you'll see them if you want to look at them more, but this is basically just showing the sort of plateau of ozone starting in 1989. And again, the recovery's been very, very slow, but it's happening. So this is a plot of UV index. This is basically how much sunlight, harmful UV rays we would be getting. And the higher up you go, the worse it is. And we started up this trajectory, but we were on this trajectory if nothing had been done. If Roland and Molina hadn't recognized the problem, and if the world governments hadn't acted, we would be way up this curve and heading higher, and the incidences of skin cancer and other issues associated with high UVA and UVB would be rising all the time. It'd be a big problem. Paul Crutzen, who won Paul Crutzen, Nobel Prize in Chemistry for his work on ozone depletion, right before his Nobel Prize acceptance speech, he did a little back of the envelope calculation, and he wondered what would have happened if, instead of using chlorine, which is in the same it's in the same part of the periodic table as bromine, and he said, what if we'd used bromine instead of chlorine? What if we'd used if bromine fluorocarbons had been developed rather than chlorine fluorocarbons? And based on his calculations, the bromine would have eaten, would have attacked the the ozone so much faster than chlorine did, that we would essentially would have been completely stripped, or we would have dramatically reduced the amount of ozone in the atmosphere before we even knew there was a problem. And chlorine and bromine act chemically similar. So we really kind of just got lucky there. As he says here, it was by more luck than wisdom that this catastrophic situation did not develop. All right, so that's that. And I will stop the recording.